Hello and welcome back to Kim Reads as we continue with Rosalind Franklin. Chapter 4, Learning about X-rays. Rosalind went to France. She spoke French well and had always loved the country, which she had visited before the war. She once told a friend that she sometimes felt more French than English. At least, she often got along better with French people. Rosalind found that French scientists enjoyed arguing, just like she did, and they didn't have many silly ideas about how women should behave. Rosalind worked in a laboratory in Paris. Unlike London, Paris hadn't been badly damaged during the war. All its elegant buildings were still standing, but food and housing were scarce and expensive. Rosalind found a small room for rent on the 5th floor of a building. She rode her bicycle along the river to work each day. She was learning a way to study new molecules called X-ray diffraction. There were different kinds of energy. One type, electromagnetic energy, exists as waves. Think of the waves you might see in a puddle of water on a windy day. The surface of the water moves up and down. The waves have a high point and a low point. If you measure the distance between the high point of one wave and the high point of the next wave, you get your wavelength. If you measure how fast the waves move, you get their frequency. Waves with short wavelengths have high frequency. Waves with long wavelengths have low frequency, like this. Just like water waves, electronic magnet waves have wavelength and frequency. There are also many different kinds of electromagnetic waves. Radio waves can have wavelengths several feet long. They have low frequency. Visible light has medium wavelengths and medium frequencies. X-rays have small wavelengths and very high frequencies. Diffraction is the way waves act when they hit something. They bounce back. They bounce off each other and change. Scientists already knew that X-rays could be used to make photographs of people's bones. The X-ray's wavelength was so small that it could be thought soft tissue like skin and muscle. X-rays bounced off harder tissue like bones. The bouncing wavelengths could be captured on a photograph. It was the first time doctors could see inside a human body without cutting into it. Not long before Rosalind Franklin went to France, scientists realized that X-rays could be used in another way. Their wavelengths could be made smaller than the distances between atoms and a molecule. If you fired X-rays at a molecule and looked at a pattern of the waves that bounce back, you could learn something about the structure of the molecule. This was very important. Scientists already understood the structure of many simple molecules. After all, when a molecule is made of only a few atoms, there weren't very many choices. A water molecule, for example, was made 2 hydrogen atoms and 1 oxygen. Hydrogen atoms can only be attached to one atom, so the structure of water had to be HOH. Penicillin, the first antibiotic, is made up of 16 carbon atoms, 18 hydrogen atoms, 4 oxygen atoms, 2 nitrogen atoms, and 1 atom of sulfur. Imagine these atoms as a pile of 41 Lego bricks. There are hundreds of ways they could fit together. But until scientists knew the correct structure of penicillin, they wouldn't be able to manufacture it, and penicillin had become a very important medicine. X-ray diffraction revealed its structure. The structure of penicillin was discovered by another famous British woman scientist, Dorothy Crowfoot Hodgkin. She would win the Nobel Prize in Chemistry in 1964. X-ray diffraction was new and difficult to do. Everything happened on such a tiny scale. Remember how small molecules are? Penicillin molecules are pretty big, and still one shot of penicillin contained 5 trillion, whatever this number is, 5 trillion molecules. X-ray diffraction meant taking photographs of waves bouncing in the spaces between the atoms of the molecules. Rosalind wasn't studying penicillin. She was back to studying different kinds of coal. Now she was using X-ray diffraction. When she was successful, she ended up with a photograph that looked like this. These photographs gave important information to the people who understood them. Rosalind had to sit down with each photo, measuring the distances and angles between all dots, and do a lot of math. Eventually, the math would lead her to the structure of a molecule. It was not easy and took a long time. Dorothy Crowfoot Hodgkin, who discovered penicillin structure, worked 35 years to discover the structure of insulin, another important molecule. Rosalind enjoyed X-ray crystallography, which was the name of this new branch of science. It was picky and precise. It suited her strengths. But the early diffraction machines leaked radiation. This could be dangerous. X-rays were small enough that they could enter cells in the human body and make tiny changes. Too much exposure to X-rays caused cancer. Scientists knew this. They wore badges that measured how much radiation they were exposed to. If the badge showed they were over the safe limit, they had to quit working for a few weeks. Rosalind was unhappy when overexposure kept her away from the lab. She wasn't too worried about radiation. She wanted to work. Rosalind thought about staying in France, but her family missed her and she missed them. In 1951, after 4 years, she left Paris and went back to England. She took a job in a research laboratory at King's University in London. There, she helped make a discovery that changed the world. She used X-ray diffraction to photograph DNA. And that's the end of that chapter. See you later.